That was awesome! Let's go! Go, 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 come on!
Do we just leave him? He'll catch up.
Sorry!
Remote driving system activated.
Wait, which side of the road is it?
For God's sake, just drive.
Okay, calm down. Hey, what was that?
Don't worry about it. You're doing great.
Hey, look at your suit. You've been taking bullets, charging it up with kinetic energy.
Put around the truck. Ready, go!
You show off.
Could Black Panther really have sent the car as high as he did? In a clip seen before, Shuri states,
The nanites absorb the kinetic energy and hold it in place for redistribution.
so to answer our question, we must determine if the potential energy of the car at its highest point equals the total kinetic energy Black Panther accumulates, since according to the law of conservation of kinetic energy, energy cannot be created nor destroyed. First, let's calculate the total kinetic energy Black Panther accumulates. There are two ways he does this, by jumping on cars or taking bullets. In the first scene, Chadwick Boseman jumps about 2.5 times his height to land on the car. When he reaches the car, all of his potential energy he has accumulated as he has jumped is converted into kinetic energy, since from his maximum height, he is only accelerating downwards due to gravity. Therefore, our first component of kinetic energy is equal to his potential energy, which is defined as mgh, m being Chadwick's weight of 88 kilograms, g being 9.8 meters per second squared, and h being his height, 1.83 meters, times 2.5 minus the height of the 2018 Lexus LC he jumped on, 1.345 meters. This comes out to be 2,367 joules. Next, Black Panther jumps between cars 3 times. Using the same MGH principles earlier, we can find the Y components of kinetic energy, assuming he jumped about 0.2 meters to be 172.5 joules. For the X component of kinetic energy, we can use the direct formula for kinetic energy to calculate energy. The formula is 1/2 mv squared, m is still 88 kilograms, but how do we find v? Since velocity is defined as the change in displacement over the change in time, we can estimate Black Panther traveled about the width of one 2019 Lexus, or 1.92 meters in 1 second. Now that we know the velocity is 1.92 meters per second, the X component comes out to be 162.2 joules. Adding our two components together and multiplying by 3 jumps, we get a total of 1,004 joules. Finally, we must account for the bullet shot at the hero. The gun most closely resembles an M16. In its standard model, an M16 shoots .0036 kilogram bullets at 990 meters per second. Using the same kinetic energy formula, 1/2 mv squared, we get a total of 1,764 joules per bullet. When analyzing the sounds of the scenes in slow motion, there is found to be a total of 94 gunshots, where the shooter had aimed in the general vicinity of Black Panther. Of these, 12 shots hit the ceiling and never passed through, and 11 are visually seen not to hit. When the kinetic energy of one bullet is multiplied by 71 possible hits, we get 125,200 joules of kinetic energy. Adding all 3 parts, Black Panther accumulates a possible 128,600 joules of kinetic energy. Now to calculate the potential energy of the launch vehicle at its maximum height. Remember, this value must equal our previously calculated value since energy cannot be created or destroyed. When attempting to calculate height in order to satisfy the equation used to calculate potential energy mgh, it seems very hard to do this. Time is distorted and there's nothing to compare the vehicle's height to while it's in the air. Luckily for us, we do receive a point of reference, being the white lines and link between the lines on the road. Velocity is assumed to be constant throughout, since the cars were going the same speed during the chase and right after the vehicle lands and is moving relative to Black Panther's. This means that while in the air, the opposing vehicle must still travel the length of a light road line or between it in the same amount of time as if it were on the road. When analyzing the scene, it can be found that the vehicle travels a white line in 0.452 seconds, in between white lines in 0.327 seconds. And since we see the vehicle travels 3 white lines and in between about 2.5 white lines whilst in the air, we can determine the air time of the car is 2.174 seconds. Since anything thrown upwards and landing downwards at the same height has equal travel time at the top and bottom, ignoring air resistance, we can determine that it takes 2.174 over 2, or 1.087 seconds for the vehicle to land from its highest point. Using the kinematic equation, yf equals yi plus vt plus 1/2 at squared, we can plug our known values in to calculate the initial y height, also known as h, in our MGH equation. Yf is 0 since the vehicle lands, v is 0 since the vehicle starts at a maximum height, a is gravity, and t is 1.087. Solving for y, we get a height of 5.787 meters. Applying this to MGH, we get 5.787 times 9.8 times the weight of a 2014 Toyota 4Runner, 2,041 kilograms, plus the average weight of 2 American men, 179.6 kilograms. This comes out to be 126,000 joules, which is actually quite close to 128,600 joules that Black Panther's suit accumulated. This situation really could have happened, assuming the shooters are quite accurate.
This is crazy. I don't want to hurt you.
Here we go. Here we go.
Could the hammer really have sent Hulk flying at the velocity it did? To answer this question, we will use a very important principle, the law of conservation of momentum. This principle translates to the idea that the total momentum of a closed system, momentum being defined as mass times velocity of the specific object, cannot be created nor destroyed. In our case, the momentum of the hammer must equal the momentum of the flying Hulk. This is assuming Thor transfers all of his momentum to Hulk, since it is already bad physics that Thor did not slow down when hitting Hulk, thus creating momentum. Let's first find the momentum of the Hulk. According to Wikipedia, the Hulk weighs 653 kilograms. Velocity can be defined as the change in displacement over the change in time. In this scenario, we will use the velocity of the Hulk between first contact with the hammer and first contact with the wall. From this reference, the Hulk flies about 9 meters in half a second, giving him a velocity of 18 meters per second and momentum of 11,754. Now for the hammer. The hammer travels in an arc or circle-like trajectory. To calculate velocity, we will use the arc length of this circle over the change in time. In about 1/10 of a second, the hammer travels 90 degrees. Since arc length is defined as degrees over 360 times 2 pi times the radius, all we need to find is r. When doing pixel comparison to familiar objects, the hammer is found to be 1.3 meters. The arc length is therefore 2.04 meters and velocity 20.4 meters per second. Using the law of conservation of momentum, we can set 20.4 times the mass of the hammer equal to 11,754. The mass of the hammer is therefore 567.18 kilograms. To see if this massive hammer is possible, we can use the principle of density. Density is defined as mass over volume and must be constant throughout a specific element or alloy, such as iron. We already have found the mass of the hammer, but what is its volume? The hammer most closely resembles a rectangular prism. When using pixel comparison once again, we find that its volume is 0.58 meters times 0.34 meters times 0.34 meters, coming out to be 0.067 meters cubed. When applying this to the weight, we find that the density of the hammer is 8,465 kilograms per meters cubed. All the metals fairly close to this density are forms of brass, bronze, copper, cadmium, cobalt, and columbium. Yet all of these either do not match the color of the hammer or are irrational to use in a hammer. So unless the hammer is painted on or is a very special alloy, this is bad physics.